Hello everyone, this is Wilson here. Today I'm going to talk about an integral that requires a trig substitution. And you may ask, we don't really have a square root here. Can we really use the trig sub? Actually, we can, right? Who says we cannot without the square root? We can still use the trig sub here because you can see that it actually has the form of a trig sub. And then so now before we get started, let's just recall something so that we can get the trig sub done really smoothly, right? So let's do this. So first, we are going to recall something right here. So what I'm going to recall is that we are having the identity, which is 1 plus tangent square theta equals to secant square theta. Okay, so what happened is that I am going to claim, okay, so I'm going to claim this tangent square theta as x squared. And do you see what's going on here? If I claim that this tangent square theta as x squared, then 1 plus x squared, which is exactly what we have right here. And so that later on can be replaced by this 1 plus x squared can be replaced by the secant square theta. Okay, so now what is our substitution? Our substitution is actually what? Our substitution is actually so that if x squared is equal to tangent squared, then x is going to be what? It's going to be just tangent theta here. And then because we are going to also define the inverse function for the tangent, so in this case, we require tangent to be 1-to-1 here. So we are going to set a restriction for theta. So theta is going to be between negative pi over 2 to pi over 2. Okay, so the next thing that we need, right, is that we need the triangle. We need the right triangle because later on when we finish the integration, we actually need to go back to convert our variable from theta to x. And so in that case, we may need this triangle. So it would be a good idea to construct this triangle at the beginning, so that it doesn't get in the way of our main problem, right? So right now we're just doing a lot of preparation on the side. So if you look at this x equals tangent theta right here, we can actually pretend that x is x over 1, right? As you can see here. So tangent theta is actually the opposite over the adjacent, right? So we can label the x as the opposite side right here. And then the adjacent side is going to be just the 1. And so what about the hypotenuse? The hypotenuse, using the Pythagorean theorem for the x and the 1, we are going to be getting 1 plus x squared inside the square root. Is that okay? So now we are going to be doing what? We are going to be also taking the derivative of x with respect to theta. And you may say, why do we do that? It's really because we need to replace this dx also. So it's not just replacing the function, but also the dx that we also need to replace when we make a substitution. So now take the derivative, then we are going to be getting dx, right? That's the derivative of x. And then what do we get here? The derivative of tangent is going to be secant square theta, d theta. Okay, so now once we have this, then we are ready to actually go back to the main problem and start doing the substitution. Okay, so let's do that. So now going back to the main problem, we have the integral of 1 over, okay, so the numerator, it's just 1, but in the denominator, then we have more stuff. So now going back to what we recall, we claim the tangent square is x squared, right? Because x is tangent, so x squared is tangent square. What happened is that this 1 plus x squared is actually just the secant square theta, right? So we can actually replace this 1 plus x squared by using secant square theta. And then don't forget that there was still a square on the outside that we did not touch, right? So just leave it as the square on the outside, and then we are going to put in that secant square theta in there. Okay, so that's not done yet with the substitution because we also need to replace the dx. That's actually really important because the dx is non-trivial, so don't forget. Sometimes people omit this dx right here when they do trig sub, and then that will mess up the whole problem because they're forgetting some details that are really important, right? So we do need to have that secant square factor in this integral here. So let's just put that here, replace the dx by that secant square theta, right? And then d theta. Okay, so now we actually have completed the substitution. And then now we need to think about how to integrate this. Okay, so let's clean up the expression first. So we are getting, going to be getting, in the numerator, we are just going to be getting the secant square theta, right, d theta. And then what about the denominator here? What about the denominator? It's going to be, let's see, so we are squaring the secant square. So we are going to be getting secant to the fourth power. Okay, so now we have this integral. So from here, what we are going to do is that we can actually do some canceling. So what happened is that we can completely cancel out the secant square theta here. But then for the secant to the fourth power at the bottom, then we can only cancel out two copies, two factors of those, right? So we're going to reduce the power so that we are actually just getting what? Just getting the secant square theta. Okay, so next step, we have the integral of 1 over the what? The secant square theta. And of course there was still the d theta on the side, right? Okay, so now what should we do next? It looks like a hard integral to compute, right? It looks challenging, but then actually remember that 1 over secant theta is cosine theta. So 1 over secant square theta is actually just cosine square, right? So that's not even difficult. So we actually are having the integral of cosine square theta d theta here. Okay, so because we have an even power for the cosine, so what do we need to do here? We got to use the half angle formula to convert this into a different expression, which will allow us to integrate directly. So what is that? That's going to be 1 over 2, okay? And then inside the brackets, we are going to be getting 1 plus, okay, 1 plus cosine 2 theta, right, d theta here. And see that this angle right here that you have is half of the 2 theta, right? Theta is half of 2 theta, so that's why it's called a half angle formula right here. And so what we can do right now is that we do not really need the 1/2, right? So we can just move it outside of the integral, and then we can focus on integrating the 1 and then also the cosine of 2 theta. Okay, so going from there is actually pretty easy because integrating the 1 would be easy. Integrating a cosine, right? Just the cosine, there's a little bit of chain rule involved right here, but then it would still be really straightforward to integrate. So we are getting 1 over 2, and then times, what do we get here? Integrating the 1 with respect to theta, not x, right? So you got to be careful here. It's with respect to theta. So we're getting theta right here because the antiderivative of 1 is going to be theta with respect to theta. And then plus, okay, so plus. Now, what do we get here? We are going to be integrating the cosine, which is sine, right? So we have the sine here of 2 theta. It's important to reverse the chain rule, so don't forget to do that, right? So we are going to be getting 1 over 2 right here. And then there was the, we add the constant of integration right here. We actually should put the c on the inside, but I'm just going to omit that for now. I will just wait until the end to attach the c. Okay, so now what are we getting here? So we can start distributing the 1/2, right? We get 1/2 theta plus, and then 1 over 4, and then sine of 2 theta here. Now, this expression that we have here is the antiderivative. but it's in terms of data, not in terms of x. So what can we do here? This one is actually quite simple. All we need to do is to use this here. This x equals tangent data. Okay, so if we find the inverse, then we are going to be getting what? Let's see. So if we find the inverse, it's actually data is equal to arctangent, right? Tangent inverse of x in this case. So that actually could be, it's already done, right? We already have that. But what about this one right here? What about the sine of 2 data here? We cannot really use this triangle to find an expression for this one because that's sine of 2 data. So we actually need to rewrite this into a different expression. What can we do right here? We can actually use the double angle formula. Okay, so let's do that. So in the next step, I'm actually going to start substituting the stuff back there already. So the data is actually going to be replaced by the tangent inverse of x. Okay, so we have the tangent inverse of x. Okay, and then what do we get here? And then we are going to be getting 1 over 4. Now, what is this equal to? For the double angle formula, it's actually what? So it's going to be 2 sine theta cosine theta. Okay, so that's that one right here. And that turns into this 2 sine theta cosine theta. So now we are actually ready to use the right triangle and then find an expression for sine theta and also cosine theta. And then we can cancel the 1 and the 4th also, right? So be a good idea to do this. So that becomes a 1, that becomes a 2. Okay, so do it at the same time. And so what are we getting in the next step? We are getting 1 over 2 tangent inverse of x. Okay, and then plus 1 over 2. Okay, so now the sine theta. Sine theta, based on this angle right here, it's going to be the opposite over the hypotenuse, right? So we are getting x over square root of 1 plus x squared. What about the other one? What about the other one? The other one is the cosine, right? Cosine is actually 1 over that. So we have the other one, which is 1 over the same radical, and then plus the constant of integration. And then we can actually clean up this expression right here. So what we can do is that final answer, we have 1 over 2, right? Tangent inverse of x, and then plus. Now you can see that when you multiply the two radicals together, then you're going to get a square, and then that will cancel with the square root. So you're just getting 1 plus x squared in the denominator with the 2. So we get a fraction, which is just x at the top, and then we have 2 times 1 plus x squared in the denominator, and then plus the constant of integration. Then we're finished. Okay, so that's a long problem. It has a lot of information that you need to worry about, a lot of details that you need to worry about, but it's actually not too bad. Okay, so that's it for this problem. If you like this video, please give me a like, subscribe to my channel, and share my videos to others. It will give me support to make more videos. If you have questions or have a topic that you want me to talk about, please leave me a comment. Thank you for watching this video. I will see you next time.